Today I'm going to talk to you about lazy imports and the art of interpretive procrastination. So, a little bit about me. I'm Brittany Reynoso. Hello. And for the last for the last 7 years, I've worked on the Python runtime team at Meta. And during that time, I can honestly say that I've worked on some pretty interesting projects. I spent the first few years working on a greenfield, performance-driven re-implementation of CPython called Pyro, which later open sourced as SkyBison. We changed the object model, we never introduced the guild, and we had hopes of achieving 100x speedups. And in case you're wondering what happened to SkyBison, yep, it was extension modules. It was a slow death by 1,000 cuts. But darn did we build a fast Richards machine. So once SkyBison kind of wrapped up, I made my way over to Cinder, where I had the pleasure of focusing on static Python and then lazy imports. From there, I created Lifeguard, which is a static analysis tool to help adopt lazy imports. And all of that culminated to what brings me here today. I'm a co-author on PEP 810, which introduces explicit lazy imports to Python 3.15. So today I'm going to talk to you about lazy imports, the history, why we wanted it, why you should want it, how it works, and how to use it. And I'll also be referring to some of my experience specifically within lazy imports at Meta, and I'll try and do my best to distinguish between the implementation that's landed in 3.15. So before I really dive in, first I want to take some time to set some common foundation. In case you aren't already familiar with Python's import system, here's a crash course. So when you have import food, what happens? First, Python finds the required module by looking at its built-in modules and the configured directories in system path. Next, it loads the file into memory, compiling it if needed. And finally, it executes the module, running all of its top-level code, creating functions, classes, variables, and also recursively executing other import statements as well. A single import quickly cascades into a lot of real and possibly expensive code execution. And this brings us to the topic for today, lazy imports. Lazy imports is a new feature in CPython 2.15 that allows the user to defer importing a module until it's actually used. The common example that people tend to refer to when talking about lazy imports is the CLI. Most of us here have probably used a command line interface and have experienced the pain of iterating with a slow one. For example, if you're implementing one for yourself, things start off small, manageable, you have a few dependencies. But as it continues to grow, you may find yourself spending seconds to even minutes waiting for a single dash help to tell you what to even call. And this is a great case for lazy imports. But let's zoom out more, because I think there's actually more here. My personal opinion, and yes, I'm very biased, is that I think when lazy imports truly shines is when you realize that the real power of lazy imports goes beyond any single module. For large, complex projects over time, your imports can start to look something like this. This is a real Instagram dependency graph in January of 2022, before we adopted lazy imports. So what you're looking at, if you're a little bit confused at this web on the screen, is basically the very interconnected web of dependencies that we had created for Instagram's Django tier. We were loading over 28,000 modules at startup. And it stirred up quite a few pain points for us. For developers, reloads could take up to 2 minutes. And circular dependencies became a nightmare. And once you've experienced something like this, it becomes pretty clear the status quo is untenable. So that was where we were coming from back in 2022 when we decided to take an interest in lazy imports. So lazy imports at scale, what does it look like? And again, this is talking a little bit more about the very aggressive implementation that we have at Meta, but In 2022, we started rolling out an aggressive plantation of lazy imports within our own fork, Cinder, which has since evolved into a pip installable extension, CinderX. It's open source, you can find it. But this also, to get back to Instagram, this allows for us to load 12x fewer modules. We saw 70% startup time reductions and increased throughput for our Jango servers. In addition, other executables were able to see large increases of memory usage by over 70%. Python programs that used to regularly were suddenly experiencing a whole new level of stability. Large-scale rollouts of our lazy imports implementation tended to look something like this: huge decreases in memory and wall time usage at enablement. You can probably guess where we turned on lazy imports. And after seeing what it could do for us, we wanted to share our implementation with the rest of the community. So PEP 690 was born, and PEP 690 was rejected. But it did lay some very important ground. PEP 690 was an attempt by two of my former teammates, who I hold dear, Herman Mendes-Bravo and Carl Meyer, to upstream the version of lazy imports that we were using internally at Meta. It enabled lazy imports globally with a runtime flag that made every import lazy. There were a few ways that you could mark some imports if you needed to load them eagerly, but the process was very manual. And I want to highlight some of the reasons that the PEP was rejected, because that'll become very relevant a few slides down the line. So some of the things that the steering council had issues with was that the expected behavior of Python code became very unclear. You could no longer tell when imports would be loaded. And also, the approach lacked granularity. There was a lot of genuine concern for library maintainers that they'd have to support two modes of execution: lazy and eager. And finally, the entire implementation relied on the mutation of a very core internal data structure, the dict, a very performance-sensitive, highly tuned data structure that really lies at the base of all of Python. And I'll even add my own 2 cents. It's actually pretty difficult to adopt. So difficult that at Meta, we ended up writing not one, but 2 static analyzers to detect lazy imports and compatibility. So take these dates as approximate. I have not spoken to any of the other companies to confirm, but this is roughly what I remember. So even with the rejection of PEP 690, things were changing. A foundation had been laid. Once PEP 690 was in the wild, the reference implementation the appetite for lazy imports only continued to grow. Hudson River Trading implemented their own version of lazy imports using PEP 690 as a reference. They enabled lazy imports across the entire firm. And a few years later, Google did the same, maintaining their own fork as well. And of course, we were still using our own fork of lazy imports. And not to mention all of the additional art centered around deferring import overhead, some of which was already available in Python since 3.5. But it wasn't just the big companies who were interested in lazy imports. We were just the ones who had the ability to maintain an entire fork of CPython. While the impact at scale is undeniable, lazy imports helps modernize Python and prevent the need to move into other languages to reduce import overhead and memory pressure. The thing that makes Python Python is its ecosystem. Being able to more tenably manage it not only helps companies like Meta or Google, but it also helps data scientists, scientific researchers, and other developers across many industries. Lazy imports is also a common feature in many programming languages, so bringing it to Python just made sense. The demand was there, and it was time to try again. So just last year, 7 of us got together to author what has ended up being one of the most discussed PEPs in the history of discuss.python.org. We were a group of engineers from Bloomberg, HRT, Meta, LinkedIn, and with great counsel from many others as well. We had listened to the feedback from PEP 690, and this time, we took a different approach. We went explicit. Explicit lazy imports. The behavior is local. Laziness applies only to the specific import marked with the lazy keyword. and it does not cascade recursively into other imports. A lazy import is an isolated decision each time it's used, not a global shift in semantics, with the most performance-sensitive areas of the code base being able to be focused on and optimized. The semantics are explicit. When a name is imported lazily, the binding is created in the importing module immediately, but the target module is not loaded until the first time it's used. Lazy imports are controlled. Lazy loading is only triggered by the importing code itself. There are no surprises. Library authors can choose to use it or not. And the mechanism is granular. Instead of a global flag that turns it on for the entire process, we've set it up such that you can adopt it incrementally, as you see fit. We want the experience of lazy imports to be optional, progressive, and truly adaptable to the needs of each project. So, in Python 3.15, making an import lazy is as easy as prefixing your existing import statement with the newly introduced soft keyword, lazy. And in case you're already wondering, what about backwards compatibility? Yep. So this is the mechanism that we ended up landing on to provide backwards compatibility with lazy imports. We've basically made dunder lazy modules a specialized container where if you save the name of the import as a string, we'll know to execute it lazily. And semantically, it'll work just the same as this. So let's go a little deeper. Let's peek under the hood. And how does this actually work? In this example, we'll lazily import a module, define a function to call a method on the imported module, and then finally call that method. Now let's walk through how the interpreter actually handles this code. So I'll highlight as I go. First, when lazy import foo is called, we create a proxy object. This is in lieu of actually loading the module. The proxy is a lightweight object that we'll use as a placeholder. At this time, foo will not be in sys.modules because it has not been loaded, but it will be available in sys.lazy modules, a new container we're exposing with this implementation, mostly for debugging purposes. Here you can see all lazy modules that have been declared but not yet reunified, not yet loaded. Next, we'll define the function. And then finally we'll call it. And this is the line where we finally find, load, and execute the module, adding foo to sys.modules and removing it from the proxy container. And if the example function call was never called, foo would stay lazy. So let's dig deeper. Let's take a look at the bytecode. How do we actually implement this? To implement lazy imports efficiently, we made small modifications to 4 different bytecodes. In import name, the lazy syntax sets a flag on the instruction top arg. The import from instruction checks whether its source is a lazy import and creates a lazy object for the attribute rather than accessing it immediately. Then, to support reunification of lazy modules when accessing objects, load global and load name will check if the object being loaded is lazy and load the module if needed. But I think there's still more here. Let's go another line deeper. How does the bytecode work with the adaptive interpreter? And I think this is kind of where the real elegance comes together. When we pair lazy imports with all of the hard work that's gone into the adaptive interpreter, these checks are completely optimized away. After observing that a lazy import has been reified, Python's adaptive interpreter specializes load global. This way, you can access the module dictionary directly without needing to check for lazy imports. I think this is a really beautiful example of how the language has evolved to make big changes like these possible. Back when PEP 690 was written, the adaptive interpreter was actively in development. This approach was not yet possible. So let's talk a little bit about adoption. Let's say you want to use lazy imports in your own code. How do you do it? So there's a few things you're going to want to look for. If you have high import overhead, slow startup time, high memory usage, you can leverage profiling tools to help you figure this out, like import time. Remember to think about also if your changes need to be backwards compatible. This is the case where you might want to use the done release modules container. And then there's two other, I'll come back to the side effects, that's kind of a section on its own. But there's two other cases that I want to highlight as well, where I think lazy imports just makes things a little bit cleaner. And the first one is type annotations. We had introduced if type checking as a way to basically allow the imports for modules that are only used for type annotations, but with lazy imports we no longer need this. It can look just like any other import, and you can defer them at runtime just using the lazy keyword. And then the other scenario that I wanted to point out is you also no longer need to manually nest your imports. You can move your import right to the top of the file, like the good old Pepe intended. Also, this is an opportunity to reduce redundancy. I chose this example specifically because I wanted to show how often when you want to lazily import modules in the way that we can do it without Pip 810, you often end up with redundant modules that are nested across functions, whereas here, things are just cleaner. But there are a few restrictions to this optimization that I also want to cover. You can't use it everywhere. It doesn't work in functions, in classes, in try except blocks. It doesn't support import star, and it also doesn't support using on the future. And there's a few footnotes. So, as mentioned, import time side effects will be deferred. And just to give you a high level of what this means, in case you're not familiar, import time side effects are any arbitrary modifications to the global state when a module is imported. This can happen in a variety of different ways. One of the most common ones, as I call out on the slide, is the registry pattern. Often this is implemented as a decorator, where someone wants to create a collection of different objects or different endpoints for a web server or something of that nature. They'll often decorate a type or a function, some sort of Python object that happens at startup, and will save that information into another module. So you can basically create a registry of all of the endpoints that will be associated. And the problem there is that if you lazily import your module, that registration will not occur until it's loaded. And maybe that's fine, but it also may not happen at all if you never load it. So the big suggestion here is to use explicit registration whenever you can. Also, be cautious when mucking with sys.modules. While it's generally frowned upon to mutate sys.modules at all, be very careful in using lazy imports. I've seen several failures in my time where people have tried to access sys.modules by basically calling get into it on a module that has not yet been loaded, but they thought it might have been. So be careful. And the other one that I want to call out is make sure you avoid implicit imports as well. Always make sure to import your submodules explicitly. But if you find that figuring out if lazy imports compatibility is too tedious, too difficult, too confusing, luckily my team and I have created Lifeguard. So what's Lifeguard? Lifeguard is a static analyzer that I've been working on with some of my peers for about the last year to detect lazy imports compatibilities. It uses side effect analysis to understand when a module must be loaded eagerly to maintain existing behavior. Lifeguard is built in Rust on top of the Rust AST and borrows some core data structures from Firefly, so it's lightning fast. We can analyze well over 100,000 files in seconds. Also, Lifeguard takes a conservative approach to analysis. If we cannot statically determine a module to be safe to load lazily, we leave it eager. This approach allows for us to easily adopt code bases for lazy imports at scale. But hand-rolled approaches by experts using proper profiling will likely be more efficient. Internally, the project is decently mature, but I do want to mention that with respect to OSS, there's still a few things that need to be done ahead of the 3.15 release, which I've listed on our GitHub, so please do be patient with us. I'm a little early, but I guess I'll just say here that calling out that it takes a village, I do want to take a second to thank everyone that made this possible in terms of getting bitten into the wild. Also, if you want to find me on discuss.python, and if you want to look at any of the, want to read more about the lazy import implementation, there's the PEP, and then also linked into the PEP, there's some of the links for the meta blogs that I used here. Yeah, also my prep. So I guess now we have time for questions.
Thank you. Thank you so much for Brittany. So we still have a few more minutes for the session. So anyone have a question or someone already? Okay, please wait before the first.
Thanks for the talk. I'm curious, when you're lazy importing modules here, have you ever run into a problem with setting the dependencies?
Yes, that is one side that did not make it onto the final. So, yes, but also lazy imports is something that can be used to help detangle circular dependencies. There are some caveats to that. It can be rather specific, but essentially, if you can finish importing your first module before the circular, you basically have to make sure that the modules do not completely rely on each other at import time, but then you should be able to actually detangle some import cycles. But at the same time, if you do that, then it will be difficult to make that module import no longer lazy. Basically, you will create a situation where the structure of your code relies on lazy imports existing and lazy imports being used. If that makes sense.
Yeah, that was my, I guess, follow-up question. What happens when you have dependency B that's dependent on dependency A? How do you reconcile which one you should load, right? Like if I'm lazy loading A, but it depends on B, and B is not loaded yet. Almost like race conditions in a way.
Yeah, it really does depend on the implementation. If it's possible to load the dependency, then it'll kind of start the percent, but it might crash.
Okay, can you be devil's advocate for a second? When wouldn't you use lazy imports? Are there any clear patterns when that's not recommended?
Yeah, so I think some of the clear ones is if there's something that you would like to happen at a specific time, basically if you care about the ordering of your imports, that's something that you lose a little control with when you use lazy imports, then that's a scenario where you would want to. If there's something that you would want to make sure is either registered, as I mentioned, the registry pattern, or if there's some connections that you need set up, maybe for a database connection or some sort of, I guess, yeah, if there's something where the timing really matters, that would be an option.
Thank you.
Hi. So I have a question about lazy imports when it comes to type hints. So I will have some classes where I'm not really explicitly working with a particular object, but I want to hint to my developer that they should be passing this kind of object to the function. And so I'm curious if lazy imports would help with that, so that way I'm not like actually importing the class and just like hinting to the class.
I mean, that would work. Like, you could do that. And basically you would no longer have to take in the overhead of importing that module, but it would just become a clear type annotation.
Thank you.
Yeah.
Hi. Question about one of the slides you had said that lazy imports might replace where you put an import inside a function body
One place where you do that commonly would be when you're mocking things as part of unit testing. And should we still continue to place those imports inside the test function body to ensure that some of the mocking happens before the actual import, or is it no longer necessary with a lazy import?
If you are defining that import to be lazy, then the mock should still hold the same as it would before.
Okay, thank you.
Great talk, thanks. And I think this may be similar to the previous question, but do you see after F810 still having use cases where you would expect to rely on like the classical lazy import pattern where you're just moving the import down into your function and conditional movement? Or do you see it fully replacing that pattern?
I think in the interim, kind of in an area where we're still very focused on backwards compatibility, it can become a little bit complicated to unwind cycles without testing an import. So I do think once we're in a world where things are maybe like the oldest supported version of 315, then there should be no reason to actually nest your imports. Unless I'm forgetting something.
Thanks.
Thanks for the talk. One question was, so once you use Lifeguard to add lazy imports to your code base, how do you make sure developers are still continuing to add lazy imports for new code? Is this run as part of like a lint step, or how do you recommend that?
Yeah, so from an OSS perspective, we're thinking of Lifeguard right now as more of a linter. One of the things that F810 also exposes is something called the filter function, which is added more for advanced users. There's a scenario basically where if you want to use a static analysis tool or some sort of other paradigm, you can decide programmatically what modules you would like to load lazily and which ones you would like to load eagerly. And that basically, so there is a way in which you could feed Lifeguard through that or any other static analysis tooling. So it kind of depends on which way you go with it. I think from an OSS perspective, it makes the most sense starting out to really use Lifeguard as a way to understand what's compatible with lazy imports and what's not. So, yeah.
Thank you.
Does a lazy import work with optional dependencies where the package is not even installed, or we still have to use a nested import?
That should work because it's only going to create the proxy and it will only crash if you try to access it.
Thank you.
So.
One more question. I'm curious, what does testing look like for this? Do you have any interesting edge cases that you have to test for? And second, in your test suite, do you have a spec related to what happens if someone basically imports everything throughout their code base? What happens?
Sure. So I think in terms of testing for this, it should be pretty normal to testing for anything else. I think probably with lazy imports more than any other features, the thing that you're really going to want is code coverage to make sure that you, or if you understand the dependency intimately, then you can understand whether or not it has subtext. But I think, yeah, testing and having strong code coverage is probably the most sound way to go about it. In terms of turning lazy imports on for everything, basically you only load what's actually executed. So by default, all your imports remain lazy, and then as your code executes, you pull in the dependencies as you need them.
Thank you.
One more. I don't really thought this through, but I'm wondering if there's any interaction between lazy importing and free threading.
Oh, good question. And yeah, this is the last question. So luckily the answer is no. It's free threaded by implementation, the design. We grab the import lock when we call the bytecode that I mentioned. So basically, loading your imports is really compatible. So, yes, we are at time.
I'm so sorry, we are out of time. Thank you so much for Brittany. If you still have any other question, please look for Brittany on the Thank you.